So we've talked about how to verify if two functions are inverses, and of course we want to get to the point where we're finding an inverse, and then of course finding the derivative of an inverse. But first we need to know whether or not a function has an inverse. So we've talked about the horizontal line test to determine if a graph or if a relation was a function. We can also use the horizontal line test to determine if a function is in fact has an inverse, because essentially what we want is we want it to be one-to-one. And of course we have talked about one-to-one before. One-to-one is that every y has only one x. So if I was looking at my mapping that I used before and I said 1, 2, 3, 4, 5, and I think my original example looked like this. This is certainly a function because every x has only one y, but this is not one-to-one because 4 was mapped to from both 1 and from 3. So in order for this to be one-to-one, we would have to have each y have only one x as well. And the way that we can do this graphically is using the horizontal line test. And if I hit 2 points with a horizontal line, then it doesn't have an inverse because it's not one-to-one. So if I have a graph, say, that looks like this, well, anywhere I draw a horizontal line, I'm only going to hit 1 point, so this one would be one-to-one. And again, that's how we can check the existence of an inverse function. If it's one-to-one, we can check if it's one-to-one using the horizontal line test. If it's strictly monotonic, monotonic means it's strictly increasing over the entire domain or strictly decreasing over the entire domain, which means it's always increasing or always decreasing. Then we know that it has an inverse. So one way to check whether or not a function has an inverse is to simply graph it, which sometimes is the easiest way. If you already have the graph or if you're able to graph it very easily, then it's pretty straightforward. These two functions, as I can see, are very similar. This one has a minus, this one has a plus. And again, I can just graph them. So this guy graphed is not strictly monotonic, meaning yes, it increases, but then it switches to decreasing, then it switches to increasing, and also it fails the horizontal line test, which is because it's not monotonic. Because if I draw a nice horizontal line, I can hit up to 3 points. Therefore, this one does not, it fails the horizontal line test, so it does not have an inverse because it is not one-to-one. Looking at my other graph with the plus instead of the minus, now as I can see, this is strictly monotonic because it's increasing over its entire domain, and anywhere I choose to draw a horizontal line, I'm only ever going to hit just 1 point. So this one does have an inverse because it is one-to-one and strictly monotonic. So obviously we want to look at this algebraically as well, in case I can't graph it or I don't have time to graph it or whatever. Algebraically, what I would do is I would find the derivative, and the derivative of x cubed plus x minus 1 is 3x squared plus 1, and I'm going to set it equal to 0. Now keep in mind why I'm doing this. Don't just say, oh yeah, when I'm doing this I have to find the derivative and set it equal to 0. Remember back to chapter 3 when we learned about all of this. What does it mean when I solve and have a critical value? Because that's what I'm doing. When I do this step right here, when I take the derivative and set it equal to 0, I am trying to find a critical number or critical value. And what that means is if it has a critical number, then it could switch at that point from increasing to decreasing. That's what I'm checking for. I'm not just randomly doing math and not explaining what I'm doing. I'm looking for a critical number to see if it's possibly going to change from increasing to decreasing or vice versa. Now, when I solve this one, I get x squared equals negative 1/3, which is obviously an imaginary number, which means there are no critical values, and so therefore it can't change, and it must have an inverse. So we already knew that because this is the first one that we had, or the second one that we had graphed before. My next example that I'm going to have you do on your own is the first example. So we already know it has an inverse, but let's see if you can show that algebraically. So here is that function. We already know it does have an inverse but let's go ahead and show algebraically. So practice on your own first, press pause, try the question. When you're all done, we'll go over it together. So again, what I would do first is find the derivative of the function 3x squared plus 1, so last time it was minus 1, here it's plus 1. When I solve this one, I don't get a negative, I get x squared equals 1/3, so x equals positive or negative 1/3. And again, then I'm just going to set up my intervals, range of values starting from negative infinity to positive infinity. I'm going to have to make my little table to show, because remember, just having a critical value doesn't tell us that it changes. We have to actually check the signs at that point. So what I'm looking for is plugging some value here back into the derivative function to determine if it's positive or negative. And because it does change from increasing to decreasing, then obviously it is not going to have an inverse because it's not monotonic. You know, I like to throw those trig functions in there just to make sure you remember trig functions and that you're paying attention. So I would like you to try this one on your own. This one should be pretty straightforward. Press pause, try the question, then press play to see how you did. So hopefully you remember at this point in your life what a sine wave looks like. And a sine wave oscillates from -1 to +1 and therefore is not monotonic, not strictly increasing or decreasing over its entire domain. Now the only way that we're going to be able to get around this, and I have a whole video on this in several sections from now, is if I give you a restricted domain. As we can see, this guy right here is decreasing over the entire domain and would pass the horizontal line test. And so if I restrict that domain, then I could find the inverse between those 2 points. But right now, because we're talking about the entire domain, clearly this is going to fail. It's not monotonic, and therefore there's no inverse.